Okay, so we have a team from Open Cosmos. Open Cosmos is a company which is providing or enabling access for common people and students like us to space. Okay, so they are based out of UK, and we have Danny here from Open Cosmos. I'll not take much of the time as we are already late. We've been working with them from a long time, and they provide us with softwares which helps us, plan the satellite missions. They do a lot of other things, but that probably Danny will explain you a better way. But yeah, so we've been working with them and using their software for our CANSAT workshops. That's how we started working with them. So hopefully we'll have so many more things working with them in the future. So I'll not take much of time. Danny, over to you.
Great, thank you for the introduction. Can you hear me well?
Yes, I can.
Great, perfect. So this workshop is supposed to be conducted by Robin and myself. I hope he can join at some point. We're having some technical issues. But yeah, so it might be the both of us running this workshop. We're planning to have the workshop split into sections, and we'll try to do it interactive. And so eventually during the break, you can make any question, anything that you would like to know in more detail, or if you have faced any issues solving some of the challenges or questions or bonus questions that we're going to be making to you. So during the workshop, we're going to be using Poll Everywhere. I don't know if you know this application, but it's just to get the session more interactive, so you can to our questions directly by logging in. So essentially, by going to a specific website, and then you will receive the questions there, and we will be able to interact over there. So we recommend you to open new tabs when we ask you to do so, and to use the online software platforms and tools that we're going to be playing around with, running simulations and doing analysis, and then answer the questions that we're going to be solving. You find interesting. And yeah, I think there is a chat. We will try to answer your questions on the go. Although a few points during the workshop in which we will stop and make sure that we solve all the questions. Okay, perfect. So with further ado, let's start. And we're going to start with a quick introduction about Open Cosmos and the HDIC, which are two organizations supporting what we call the Open Cosmos Academy and the network of Open Cosmos Academy ambassadors around the world. And this comes after an MOU that was signed at the last IAC in Washington approximately a year ago. So both organizations together to support capacity building, education activities, and basically the promotion of the space sector in general. So let me start by introducing to you Open Cosmos, who we are, what do we do. So we are a company of around 50 people, more or less. We are based in UK in a cluster, in a space hub called Harwell campus, which I would say in the European region, it's one of the most vibrant and one of the biggest ones in the domain. There are more than 100 space-related companies. There is the European Space Agency main center in the UK, the business center of ESA, and many space organizations. So there is where we have the clean room, our lab, and the main office there. And it's where we build our satellites. SMP and a space mission provider. This means the space mission from early design until the satellites burn out at the end of their mission in the atmosphere when they re-enter. So we provide full space missions using small satellites, Cubesat form factors to simplify all the technologies, the times, the costs to launch technology, sensors, instruments, what we normally call payloads to space. And we highlight the analogy between the computing industry and industry. So back in time, computers used to be huge, used to be very expensive, very complex, and only available to a few research institutions. And all that changed when a few smart guys, they gathered together in Silicon Valley in a garage, and they managed to simplify all these technologies, made them very appealing, and reduce their size, their complexity, and their costs. And the result, we see them every day. We carry a whole set of that they simplify our daily lives, and we carry them in our pockets, and we use them in our daily life. So a similar revolution has been happening in the space industry. Satellites used to be huge, very complex, very expensive, only available to top national space agencies. And all this has been changing with a whole set of new technologies, using components off the shelf, reducing the size of the satellite, simplifying all these technologies. So at the end of the day, companies like us, we are a main player in this revolution, what we call new space, that we're going to talk later on. The main idea is to enable a whole set of new applications. So the image you see in the middle on the bottom, it's our first satellite that was launched 3 years ago. And yeah, right now we are working on 8 other missions. 2 of them are going to be launched later, beginning of next one. We are enabling this whole set of new applications to improve the world we live in as well. So a bit about our mission process, and this is an example for you to see how new space companies are approaching the space industry. So normally our customers or our third-party subsystem suppliers, they come to us with a particular technology to be sent to space, and the data that's going to enable services that they want to achieve from these technologies once they are deployed in a space. So we take care of the rest. We simplify all this process, and for that we have a set of tools and platforms in place. OpenApp is one of them, and today you will be able to have a look and to play around with some of the tools of OpenApp. And it's essentially a software platform that is in the cloud and has a set of tools to run mission simulation and analysis in the first phase of the space mission, but also it has other modules such as the hardware in the loop that they interface with the hardware, what we call OpenKit, that is a satellite qualification platform. Essentially, we use these methodologies, these processes, to simplify the qualification of technologies, so then they can be integrated easily into OpenSat, into the satellite platforms, and we take care of the test campaign, launch, operations, all the bureaucratic aspects of it on behalf of our customers. So at the end of the day, using the same online platform, OpenApp, the users can get the data and operate their payloads once it's in a space. So that's a bit about OpenCosmos. And now about HDIC. As some of you might know, it's a global organization. I would say it's the biggest organization of students and young professionals around the world. It's linked to the United Nations. And essentially, it's a huge network which has a whole set of working groups in different domains. They are very active all around the world. They organize a whole set of events, and they support a lot of initiatives to bring the space closer to the society in general, and basically to do research in many areas. So there are tens of thousands of members globally. We recommend you to enroll by going on the website. If you are below 35 years old, it's straightforward, it's for free. You can just log in and create an account and become a member straight away. They have presence in more than 150 countries worldwide. They offer scholarships to attend events, international events, such as the IAC, the International Astronautical Congress, which is one of the biggest ones that happen every year. And right now it's happening this year edition. It was supposed to happen in Dubai, but it's being moved to online. So have a look to their website, because there is a whole set of presentations, panels, workshops, papers presentations, poster presentations. And this year it's for free and available online. So we recommend you to join, and HDIC is leading some of these activities. So we recommend you to join activities as well. So there are more than 30 events. I'm sure that much more than 30 every year happening around the world. Now, due to COVID, most of them have been moved to online events. And as I mentioned, there are different project groups that you can get involved in some more specific areas. So you can get more knowledge, you can expand your network, and essentially you can get a much better overview of the space situation, the space missions that are happening, and contribute to some of them. Right. So that's a bit about the introduction of the two organizations that support this particular workshop and this kind of activities. So we are going to jump now into the content of the workshop. And for that, we're going to ask you to open another tab. So if you could perhaps open a new window in your internet browser. We recommend you to use Google Chrome, but Mozilla Firefox should be working fine as well. And the same for Internet Explorer or Edge, that nowadays it's also available. So we would ask you to open a new browser and put in this new browser paulev.com/OC500, the link you see here. I might write it here in the chat so you can click at it easily. So the link is Paul everywhere. Let's see. Paul EP. Yeah, and I don't know if Robin is available here, but if you can help me out with future links, because we're going to be sharing some links for BApp and so on. OC500. Okay, so I'm posting here the link. So you can just click it straight away. And we're going to be using this link across the workshop. So feel free to keep the tab open in parallel, because we're going to be using it across the session. Okay, I think we got this. Let me paste it here. Yeah, thanks. Thanks for that. So yeah, if you click the link, you should be able to access, and we would like to understand which is your level of space mission design. If you've heard about this before or not, if you are totally new to this space mission analysis and simulations, and essentially to design a space mission, or if you heard about this before. Okay, I see a few answers already. We're going to leave a few more seconds to understand what's the level of the audience, because we can tailor it and go into more detail or keep it a bit more generic, a bit more of an introduction. At the end of the day, you will be able to go into as much detail as you want. So don't worry about that. We can also provide further information after the workshop. But this is just to have a better overview before the workshop and after the workshop, so we can assess if you've been progressing well, if you've been following well, and if you've learned something across this 1 hour and a half that we have ahead of us. Okay, I see a lot of numbers dancing. I see the level is between 1 and 6 and 7, so we're kind of an average classroom, I would say. That's good. So I hope that by the end of this session, some of these 1, 3s, 4, 5s, they move to 6, 7, or 8, 9. So let's see if you manage to get more confident in all these topics. Perfect. But there's a bit of a spectrum. I see also quite some high marks as well, and so on. So that's great. We have a kind of a large variety in this session, in this workshop. So the purpose from our side for the next hour and a half, more or less, is, I don't know if you've seen Matrix, the movie. It's trying to transmit to you, trying to transfer to you as many concepts, as many tools, as much knowledge as possible in how to design a space missions and how to use some of the tools that we use to design a space mission. So we're going to be following this table of contents, going from introduction through mission concepts. So we're going to be answering why do we want to launch something into space, what is the purpose of it, what are the objectives of it, the timeline when we could be realistically launched into space, and which would be the phases to develop the space mission. And we're going to touch base on the mission requirements as well. And then we have a full section where we're going to do the break to answer the how. How could we do this? How could we launch a space mission? And this touches upon the payload. What's the payload? What's the platform? We're going to give some examples of subsystems as well. We're going to touch base on different orbits, on choosing a ground segment, the launch of spacecraft, and then space load, that is also quite important. So in these stages, we're going to present you some challenges, and we're going to ask you some questions. And we're going to give you also a worksheet so you can have it for you, and you can solve future challenges in the future. You can use this material as well on your end. Perfect. So if that's okay with you, let's jump to the content of the workshop. Feel free to post any question if you have in the chat. We'll do some stops, as I mentioned before, to answer your questions. Great. So about the core of the workshop, let's jump into the introduction. What is a space mission? A space mission is to design something. We want you today to design something that when we were supposedly launching it into space, would collect data that is useful for our purposes. And we're going to define these purposes later on. So this is an overview of a top-level definition. And to answer why space, excuse me, we could be willing to go to space for many reasons, but we want to highlight the Global Sustainable Development Goals, the SDGs, because there was recently a report by the United Nations that 17 SDGs, Sustainable Development Goals, to more than 50% space solutions are going to be key to solve more than 50% of them, if I'm not wrong, and to more than 20 or 30%, space is so important that they cannot be fully solved at a global level without the space technologies. This means that a few of them can only be effectively fully tackled and solved by using a space technology and having this overview. This goes with monitoring the climate, Earth observation, remote sensing, and so on. But we want to give this importance to this point because by using space as a tool, we can solve or help solving some of the global challenges we are facing nowadays, that they are changing the world we live in, and we really need to enforce, and the United Nations is putting a lot of efforts and enforcing new solutions, new applications to support solving some of these global challenges that we are facing as humankind. Some of the examples for these are the ones that you see here: to reduce the poverty, to improve the health, and obviously to monitor and support reducing the impact on the climate change. So these are just 3 examples of this, but there could be many more. And to put us in context regarding where we are now in the space sector as of today, we normally talk about the 4 space eras, or at least the European Space Agency likes to put it this way. The first era was a bit led by the scientists Copernicus, Kepler, Galileo, and so on. They used to look at the stars with their first telescope and their first predictions of what was going on. So we got more information of what was going on, which kind of orbits perhaps, what were the planets, stars, and so on. The second revolution was led by a bit the space race between the US and the USSR. You all know that we finished landing on the moon. The third revolution, it's led by these global international agreements to have a permanent presence in space, driven by the ISS, the International Space Station. So that's brought a new level of collaboration globally and constant presence in space. And right now we are in space for 4.0. It's led a bit more by the commercial actors, and you've probably heard about the SpaceX, Blue Origins, and many other companies that right now are leading also in some segments of the space sector. And we are in this a bit of a new era of space, in which there's the new commercial players, there's this new space that I'm going to introduce now, and the paradigm of the space it's a bit broadening the spectrum of people that can access it, and there are much more players. So there are more players, more missions as before. The use of components off the shelf, new technologies allows to simplify things, shorten timelines, and lower the cost, so more people can get involved into space. And Open Cosmos is one of the players in this new arena of Space 4.0. So there's been a bit of this shift that you see here on the screen in paradigm in the space domain. So normally, as a baseline, this is difficult, obviously, to put this, just specific numbers, but just to put you in context, normally missions used to cost, typical missions, more than units of millions or tens of millions. They used to go even to hundreds of millions. Development times were a few years, if not tens of years, if they were big scientific missions. And right now, with the small satellite missions, we see that as a baseline, missions, they don't cost millions or tens of millions anymore. They cost hundreds of thousands, perhaps, so 1 or 2 orders of magnitude less than a few years ago. And the development time, it's not like tens of years, dozens or half a dozens of years. It's a year, perhaps 2, or even down to months, maybe 10 months, 9, 10, 11 months. So we see missions that are being launched much faster with the technologies that you are going to play around today. You will see that are much more simple to speed up things when designing a space mission. And just to put you in context of how things look in space, this small satellite in perspective of a big satellite, obviously the capabilities are not the same, but we are starting to see that by going to lower orbits, we can, and deploying constellations, we can start getting some added value, some relevant information that in the past was only available exclusively for big, expensive satellites. So that these are a bit of relative dimensions of how these two different form factors of satellites could look like, or that they look like once deployed in space. And a graph to put all this in context, you see that now there are much more players in many countries right now. You see in gray the others. So before, as I mentioned, it was mainly the sector was mainly led by the United States and the Soviet Union or Russia. And in the 90s or so, that thing has started to change. And right now, as you can see, there are much more players in the space industry from many countries around the world. So it's become a much more global spread set of efforts that we are pursuing globally. Right. So let's move to mission concepts. So let's move to designing our space mission and answering why we would like to go there. So I'm going to ask you now to go to this poll everywhere. We normally differentiate between communications, missions, Earth observation or remote sensing, and then more on tech development or research and exploration. So these are normally the three main topics in which you could classify any space mission that is launched to space. So normally they are separated, or you can do this exercise of separating them in these three topics. As an example of communications, you could be providing global satellite phone coverage. So communications, these falls, other examples are IoT, communication missions for to connect with nodes on Earth. An example of Earth observation could be to monitor the rainforest or deforestation in different parts of the world. So essentially to observe the climate and to monitor the natural assets. And a third example could be to demonstrate technologies, for instance, to go to the moon. So before we go back now to the moon, to have more human presence to the moon, we could be sending more technologies over there or do research in specific technologies before going again. So I'm going to ask you to choose one of these three topics that I just presented. So we're going to go into more detail in developing a space mission in one of these three topics. So we're going to work on the requirements for one of the missions that we're going to choose now all together. So I'm going to ask you to decide in one of the missions that you would like to work on in the next half an hour or so that we're going to be iterating now. So I see that some of you want to do research and exploration, so study effects of macro on human cells. So do a bit more research on these lines. Some of you want to conduct some Earth observation, Amazon rainforest deforestation monitoring, so to monitor the Earth, which is quite relevant nowadays with the climate change. So by putting cameras on optical systems or some instruments to monitor the Earth. There's some people that hasn't done its mind in communications or not. That could be to provide global IoT coverage, as an example. So monitoring with different nodes on Earth, different parameters that could be linked to pollution or to other things. Okay, so it looks like we have a winner. Thanks for your prompt answer. So we're going to move on with research and exploration topic, vertical, let's say. And we're going to focus, so we're going to try to do an exercise to design a mission that has an effect, so to study the effect of microgravity on human cells. So the purpose would be to sending human cell, bones, different human cells, and study how the microgravity or the radiation is impacting their growth, for example. So we can better assess the impact of bringing humans to space and to deep space out of Van Allen belts, for instance. Perfect. So let's move on about when we could be conducting this mission. So as I mentioned, with the small satellite missions, we could be conducting a missions in a matter of 10 months, perhaps 1 year. So what you see here in yellow could last 1 year, maybe 2 max, of development of the mission until phase D, that is where normally the launch happens. And then in phase E, when you see operations, that could be lasting as a baseline normally 2 years, 3 years, 5 years, maximum 7 years, I would say, with the small satellites in low Earth orbit. So the total yellow length span could be around 5 years, 7, 8 years maximum. And then decommissioning could be happening in the following years, depending if we have a deorbiting active mechanism or not. But just to put you in context, that until phase D, we could be developing our mission in 1 month, in 1 year, or in 2 years if we do things right and we have the right tools in place. And in the y-axis, the workload shows where we would be spending more in developing our mission. So today we're going to focus in phase 0, phase A. We're going to do some requirements definition. We're going to do some preliminary designs and run some simulation and analysis. So we're going to focus in the first phases of a space mission. The second phase would be, or second area of action would be phases B and C, that they start touching more on the hardware. So especially in phase C, when you have the PR, the critical design review, it's where you see the workload of manufacturing and testing takes more importance. And it's where normally you procure all the hardware and you play more with the hardware. And as we don't have the hardware today, we are not in a physical place today altogether. We cannot plug the open kits, the satellite qualification platforms, and play around with the hardware. So we will do it online with OpenApp, that is this online software platform that I introduced before. So just last thing here in this slide is just to mention that there are a set of documents, set of documentation that needs to become fulfilled and defined. These are simplified using small satellites. So There's not too much of a bureaucratic showstoppers or blockers across the process. So here you see a highlight of some of these documents, PDR, CDR, TRR, that define some of the key milestones when developing a space mission that we're going to simulate today. And obviously, the launch campaign is a critical aspect when you launch satellites into space. So as I mentioned, we're going to be focusing here in this blue line and in this red line today. So we're going to do a preliminary exercise, a bit of an exercise on phase 0, phase A. Perfect. Let's move on then. So we're going to be defining the requirements of our mission. So please make the exercise of focusing on the mission we selected. We selected this biological research mission. And we want to define a set of requirements here. So I'm going to be asking you to answer some of these things, some of these requirements that you see here. The requirements can be, and specifications can be defined in functional, so they can be divided in different ways. Some of them are functional, operational, or some of them they just suppose constraints to the mission. So we should define which are the main parameters we want to measure, which is the coverage, or in which areas perhaps we want to switch our systems, our sensors on and off. What could be the duration of our mission? So how long do you want your mission to last? That could be maybe a few months to explore what's the impact of the cells, how are the cells evolving with radiation or without the radiation, with microgravity, and so on. The availability of it, how fast do we need this data? Do we need it every second or every minute or every hour? Or perhaps every day it's okay, or every week or month or year. So we should touch base on that. For a mission like that, I'm going to give some keys here regarding the biological mission. That could be every few minutes, every hours, perhaps, and the mission lifespan a few months, maybe half a year, 1 year. Normally, the biological components, or the biological cells, are quite difficult to keep them alive for long periods of time. So perhaps our mission lifetime would be a bit shorter than 5 years, probably. It could be a few months, perhaps 6 months, 1 month, or a few weeks even. The cost, what's our mission budget? That's a tricky one. So let's define that as a baseline. A mission like that for a standard 3-unit satellite mission could be 500,000 euros or pounds or US dollars, and as an example. And the schedule, when would we want our mission to start? And if we are in a rush because we need to send humans fast, so we need to do research fast, that could be we need to launch so Q4 2021, so in a year from now. If we're not that in a rush, maybe we could have more flexibility. So, but let's put it. I'm going to put some parameters here. So let's put it end of next year. We will be launching our mission with $500,000 budget and the durations I was saying. So I'm going to ask you to answer at least 3 of these requirements that I was showing. So the question here is, what would you like to measure in such a mission? So imagine we send some human cells to space to study the effects of microgravity and the effects of radiation, for example, in human cells, in bone cells, for example. So what would you like to measure there? This is a critical question for any space mission. And the reason why I'm saying that is because whatever you would be answering here would define the rest of the mission, the shape of the satellite, the configuration of it, and everything else. Because these parameters are going to be defining the payload, the sensors, the instruments that we would be using for our mission to be successful. So if we want a successful mission, we would need to measure this. So very good. I see microgravity here. So we would like to measure the microgravity levels, the exact microgravity levels next to the cells to understand which is the impact of it. We probably would be having cells on Earth, so we could be comparing the samples on Earth with the ones on space. So we would be measuring microgravity, the number of cells, for example, the division of the cells, so how many of them are dividing, are going through standard processes, which ones not. Its nutrition, the color, I see the white here, So the color of them, if it's changing or not. So we might need a camera or some kind of image sensor to see the color of it and to measure the growth. So I see here growth, which at the end it's a measure of distance. So we would be measuring, and here try to make this exercise of focus on the physical parameters. So microgravity is clear. So the G's, the levels of meters, seconds squared, levels on this, the number of cells. So for that we would need an imager, and we would need to measure physical properties. So dimensions, sizes, and we would be probably needing a camera. So this camera, we should define which frequencies we want to gather in these optical instruments, perhaps. So which frequencies are okay for us. Maybe we would be painting the cells so we could count them easily. So we would be counting number of cells, radiation, very good one. So we probably would need a counter there to measure the radiation levels there. You mentioned the health. Health is not a physical property, so try to make the exercise whenever you design a space mission on thinking on the physical properties. The exact, if it's a distance, if it's temperature, if it's humidity, if it's radiation. So knowing the units and knowing which exact parameters would you need for that. So I see really good ideas here, really good parameters to measure for our biological mission. So very good done, very well done, very good some of these points. Yeah, radiation, sowing. Yeah, I think I much highlight most of them. So well done. We have some of the things we want to measure: the microgravity, the number of cells, its color, its size, and so on. So we have a set of, we could be defining a set of requirements on all that. Well done. Let's jump now into which areas perhaps on Earth. So it would be a small satellite mission. We would be going to low Earth orbit. Would we have any requirements in terms of when we would like to switch on our instruments, and in which areas we would like to do so? Exospace could be one areas or some of the layers. Maybe we would like to go above Van Allen belts, so have perhaps a constellation, one mission in low Earth orbit, that we have more protection of them with the magnetic field of Earth, and maybe we could have another set of samples with another satellite, another mission in higher orbits of Van Allen belts. So this way we could compare the cells above Van Allen belts, so more into deep space, one perhaps in low Earth orbit, and then some samples to the surface of Earth. So perhaps we could have these 3 samples that we could compare, and maybe another one sending a small satellite to the moon or to Mars. So we could be comparing this human cell performance on Mars, for instance, on the moon, over the Van Allen belt, let's say in middle Earth orbit or in geostationary perhaps, and other ones in low Earth orbit, so closer to Earth. Okay, so high Earth, the magnetic field is key here if you want to measure the radiation and its impact on the solar cells. So I see here ozone, the planet, water. So here is more, this question is more about the geometry of the mission. So for Earth observation, we would like to perhaps take photos or switch on the payloads in specific areas, in the Amazon forest, for instance. Communication missions, maybe we would like to switch the payloads, the instruments on over cities, perhaps, or over isolated areas only. In this particular case, maybe we will be switching on and off, perhaps over the anomalies, the Atlantic anomaly, maybe, to see if that has an effect on the human cells. So we could be sending it into Titan. I see here different orbits, magnetic regions. So we could be switching on and off in different magnetic regions, right? Into deep space, into outer solar system, into Jupiter and others. So we might be willing to go. Perfect. So well, these are all valid. So let's choose a constellation of satellites sending cell moisture. So sending our experiment to Jupiter, to Mars, as you put it here, in low Earth orbit, and in different places where magnetic field of Earth is different. So well done, we have defined this constellation. And now let's go to the last one, the last requirement to do this brainstorm exercise to define the requirement. So how often, how fast do you need the data to be obtained? So if we're sending one satellite into Jupiter, another one to Mars, to the Moon, to MEO orbits or above Van Allen belts, and others to LEO orbits, how often do you think that we should be monitoring cells? Would we need it every microsecond, every second, or perhaps every minute, or every hour, or a few hours, days, or weeks, or years, months? What do you think? So every day, I see here that's the winning one. The more you click on or the more you write previous answers, the bigger the word it gets. So the more consensus it gets. So I see every day it's the consensus. I see some speeds here. So 3 gigabytes per second. That's more on the data. I'm going to touch base on that. So we're going to do link budgets and power budgets later on. This is more about how often I want to switch on my payload or my instruments. We defined a radiation microgravity sensor. We defined an optical to measure the growth of the cells, the quantity of them, and so on. Okay, so every day, microseconds. Microseconds might be too low. It might generate a lot of data, and I think that biological reactions or processes happen a bit slower in general. So I guess that you are right. Every day, so days, I would say hours, days are a good measuring for that. So that's a good number there, I believe. So let's say so every day, every few hours, we're going to be measuring our cells, our instrument, our samples that we defined before. Perfect. So thank you very much. I think we finished doing a brainstorm on requirements. So we kind of have a mission well defined. And now we're going to jump into the how before we do the break, perhaps. So we're going to do a break in a bit. Before that, let's jump into what's the payload and the platform that they define the spacecraft. We've been defining it already with these sensors and these constellations that we talked before, but I'm going to give you some examples with the other two cases that we haven't selected, which are the Earth observation and the telecommunications, the communication side of things. So these are examples of some of the payloads that we could have chosen in other missions, perhaps that we could have been defining. We focus more on the research and exploration. So this is just to give you an example of different instruments in all these three verticals. You see here in Earth observation, we could be having microwave sensors, UV sensors, radar, different thermal infrared, different frequency measurements. In communications, we could be having reflectors, relays, lasers, antennas, transceivers of many kinds in different frequencies as well. And in the research domain, we could also have telescopes, gas sensors, X-ray imagers, thermometers, spectrometers could be perhaps used for the mission that we selected. And yeah, these are some of the topics that we could be perhaps playing around with in different in other missions. But I just wanted to show you how things could look more realistically in future phases down in the process of developing a space mission. And I think that if we go back in the biological one, if I select here, you might be able to see some examples. Otherwise, I'll show you later on how different payloads could look like these of three verticals. We will be answering to define a payload these 4 points, these 4 questions here. So which will be the function, how it will be controlled, connectivity of it, and specifications regarding objectives that we've been already discussing. Perfect. So that's what concerns the payload. And regarding the platform, there are a whole set of subsystems that we should get involved with. I'm not going to go into a lot of detail into them because we could be doing one workshop for each of the subsystems, but just to summarize them, There is the control subsystem, normally called ADCS, AOCS, so orbit, attitude, determination, and control systems. Those normally are led or are composed by reaction wheels, such as the ones that you see here as an example, or magnetotorquers. So we use the magnetic field of the Earth to orientate the satellite and have the right attitude. For our mission, that would be important because if we want to have the right levels of microgravity, we don't want our satellite to spin around because that can generate accelerations. So we want to make sure that the satellite is stable and the microgravity levels are exactly as we want them to be. There is a power control unit, what we call normally the EPS, so we regulate the power, the voltage, the intensity, so the payload and all the instruments are well supplied, and we obtain all this power with solar cells normally. So we obtain this solar energy from the sun, we store them in batteries, so when we are in eclipse or when we need extra power, we can use it. So that's a very important system as well. And then in the onboard computer, we have the brain of the satellite. So here is where all the processing is happening to control all the subsystems and monitor the payload, the communications, and control absolutely everything. And on the communications, there are antennas, normally patch antennas or deployable antennas, to communicate and to send all this data that we would be obtaining down on Earth, and to receive also uplink commands from Earth. The last bit is the structure. So the structure keeps everything together. It plays a big role in the thermal performance. So we don't want things to get super hot or super cold. Some of the systems are passive. Some others are active in terms of balancing thermally the satellite. And the structure is very important in that regard, to keep everything together and to accommodate the deployment of solar panels or other things that might be popping out, antennas and other things that might be popping out from the satellite once it's deployed in space. Perfect. So we've been having kind of an introduction to the payload and the platform. Here, just to highlight that the space environment, it's hard. There is radiation, there is vacuum, there is huge thermal gradients of 100 to 200 degrees, depending if you are in the shadow side of things or in the illumination, in the sun illumination side of things. The loads and vibrations during the launch are quite tough as well. So you need to pay attention into all these things, and you need to qualify for the space environment. So it's very important that you keep all this in mind to make sure that your satellite is going to be functional once it's in this harsh environment. Perfect. Let's do a quick pit stop here. If you have any questions, feel free to write them here, as we are approaching now the break. And otherwise, feel free to put them in the chat so we can move on straight away. If you have any questions, feel free to use the chat. I will try to monitor it quite frequently. Perfect. We have here a question here with the path of the ISS. It's not a circular path. The ISS is quite a circular. It's quite in a circular orbit. And this question is perfect. It's great because the exercise we're going to do now, this hands-on activity, it falls on the ISS. So you will have to run a simulation of the ISS right now with this online software. So you will be able to answer yourself the question. You will see that the ISS falls under eccentricity 0, more or less. So it's quite a circular orbit around the Earth, around the 400 kilometers. But you are going to see all this now because we're going to do a simulation over the ISS, and we're going to make you some questions about that. We're going to be working on the Cubesat form factor. Yes, the image you saw before is 6 unit. And we could be working with a 3 unit or perhaps a 12 unit Cubesat form factor that it's more or less a microwave size of a satellite. Normally, up to 16 units, it's considered to be still a Cubesat form factor. Above that form factor, it's normally considered to be bigger, like another bigger size of microsat or a small sat. So the payload would be contained in 1-2 units, perhaps. We would be putting all the cells there. And we're putting all instruments to measure these cells, the ones that we've been defining, the microgravity sensors, the gigameters for the radiation monitoring, the cameras to monitor the growth of the cells and all that. Perfect. Yes, the ISS energy comes from the sun. That's why there are these huge solar panels. There is an image now that we're going to touch base, so you will see the image of the ISS and the solar panels that it has. They are huge and they can move, track the sun. And they even move sometimes when some maneuvers are happening, when the ISS raises its orbit or it's pushed. So there is no debris of the outgassing touching the panels and so on. So yeah, you're going to see that in the image later on. What are the white clouds type gas coming from the rocket during launch? That depends on the rocket. Some rockets use liquid propellant, some others they use solid propellant. So the outgassing depends on the content of each of the rockets. Right. What are the requirements for the control of the satellite and how we send it to the required place? That's a very good question. So defining the right orbit is essential, and we'll do that today. We're running these simulations, but it's also very important to keep the attitude and know where you are. And for that, we use GPS sensors and Galileo and navigation constellations that we, again, are going to do some simulations on that to know where we are. And we use the magnetic field, sun sensors, and star trackers to know exactly in which position we are in space. So that's a very important aspect of a space mission. So very good question there. Perfect. So the requirements on the control could be the stability, how stable you want your satellite to be, or if you want to point somewhere, which degrees of offset you can be of a particular point. It can be nadir pointing or pointing with other attitude loss. That's what we call normally. So we have different attitude loss depending on the payload, depending on our mission. Perfect. So how small a satellite can be? I've seen tiny satellites. There are even pocket cubes that are 5 by 5 by 5 centimeters, so they are super small. And I've seen even PCBs, or there is the Breakthrough Foundation, they have even chips that can transmit some information. They normally don't last much, but the satellites can be as small as credit cards, pretty much, and as big cars or big buses, or the ISS itself, that it has the size of a football field. We're not going to be using the SDK. The SDK, I don't know if they have an online module. We're going to be using our own online software platform that is descoped, and it's more focusing small satellites, and it's in the cloud. So we're going to be using OpenApp and the set of tools in OpenApp. So the MSD and what we call BApp, that is the previous stable version that we have in place. So we're going to give you access now into them. Okay, so what is the payload? The payload weight limits, normally this can be a few kilograms. So if we are with a Cubesat form factor of a 3, 6, or 12 unit, the payload could be a couple of kilos, 1 kilo, 2 kilos, up to maybe 10 kilos or so for maybe a 12-unit satellite mission. So we have a few kilos to play around with our payload in this exercise we're doing now. Perfect. So can closed piece can be used as antenna? Well, that's a very specific question. There are different materials to isolate thermally the satellites. Those are called the MLIs, normally the multi-layer insulation systems, but there are also aluminium shields to protect and to dissipate thermally, also different piping materials to dissipate thermally and radiate these energies thermally. So I guess the question was going in that direction. What is the use of PSLV satellite? So I guess the PSLV you mean by the Indian rocket that I think is currently still holding the record of deploying in one rocket launch more than 100 small satellites. So India has been leading a bit the deployment of small satellites in the past. So and PSLV rockets are also quite used even nowadays to deploy small satellites. Do the astronauts have to control the ISS, or is it automatic? It's quite automatized, I would say, but as always, and there is always the possibility to take control over certain aspects of the attitude and so on, similarly to what happened when landing on the moon. Which one is better, to liquid or solid? This is a very tricky one because depending on the purpose of your rocket launch or your mission, liquid can be better or solid. Solid normally has some advantages. The liquid can be reignited many times. Normally, solid, when you ignite the rocket, in most of the cases, there is no way to stop it. So the boosters that you see in rockets, such as the space shuttle, the white boosters, they work only once for a few minutes, and they cannot be used anymore. The liquid rockets, yes. The efficiencies are, so the specific impulses are different depending on which propellant you are using and so on. So that's why nowadays some rockets that have solid propulsion and some others that have liquid, and some that they use solid in some stages and some liquid in other stages. Ariane 5 is a good example of that. Also using solid boosters and liquid propulsion systems for higher stages in the launch. Difference between payload and satellite. So satellite, as you've shown in the image, is the whole spacecraft that can be divided between payload, normally, and platform. That's how we defined it. So that's how we divide it, more or less. So payload plus platform, normally they compose the satellite. The payload has normally the sensors, the instruments to measure the exact parameters you want to measure for your specific mission, for your mission purposes. Right, so I think I answered pretty much all of them. How are the instruments protected in space from radiation? By shielding them, as I mentioned before. There are different materials that are better than others, so we put panels in the sides of the satellite to protect them from radiation. And obviously, you can protect them electronically, let's say this FDIR, to monitor these latch-ups that can happen with radiation. So at software level and at electronics level, you can have redundancy, so different, like 2 processors perhaps, and different systems on that to protect from radiation effects. The weight affects the satellite, so you need to take into consideration the mass of the satellite, the inertia of the satellite for the attitude. So the weight and the mass is critical for the satellite, especially for launch. So you can have the right structure, putting all the masses and all the systems together in the right way. How to use magnet to control the orientation of the satellite. So there are coils in a similarly to the compass. So if you have a coil on Earth, as you are in microgravity, even if it's a small torque or a small force applied into your torque, into your coil, that can be used to, with time, orient your satellite and align it with your specific attitude you want to have, taking into account the magnetic field. So using coils it can be helpful to orient the satellite. What's the maximum payload that can be carried by space vehicles? That depends on the size of the vehicles. As mentioned, there are car-sized vehicles, such as some of the Sentinel satellites from the Copernicus program, and some others they are much smaller. These Cubesats can weight like a few kilograms, as I mentioned. Okay, what's the payload? Can close? Okay, I think we answered pretty much all of them. A lot of questions about Mars. I believe the Mars colony is possible. I think we might be able to see it in our lifetimes. I think we're going to reach Mars at some point eventually. I have hope on that, and I know that Elon Musk is quite convinced on that. So I think that it's possible to have a colony on the moon, on Mars, to send to have human presence there in a stable basis in the future. When it's going to happen, I don't know. There's a lot of bets here. I would say in the next 10, 20, 30 years, perhaps, we will for sure be stable probably in the moon, and hopefully into Mars. We will have had some human missions into Mars, hopefully. Fingers crossed. And we're going to be working on a Cubesat right now using the software tools, not with the hardware, because we are not in one place. Otherwise, we would bring some of the satellite qualification platforms. But right now, we're going to do this exercise remotely. Perfect. So let's do the break now. I'm going to put you the links if you want to start exploring the software tools. So during the break, you will have 5-10 minutes to play around with it. Perfect. So I'm going to leave this hands-on activity 1 on the screen. So this is about the ISS, as I mentioned. Here you can see the solar panels that gather all this energy to keep all the systems and experiments running on the ISS. So this is answering also some of the questions you had before. So I'm going to leave this slide here, and let's do a 5-10 minutes break. And for those of you that want to start exploring this online software platform called BApp, feel free to log in. During the break, I'm going to put all these links there and access it through these credentials, username Starman and the password planetmars09, all in minor cases, no capital cases. So feel free to start logging in and playing around with the software. It's quite straightforward. You will have to write your mission name, your program name, and click on Go, and then you will enter to the MSD, so the Mission and System Design tool. And there in that module, you will be able to play around and launch simulations. You have here step by step what you are supposed to do. The objective is that you answer this question in 10 minutes or 15 minutes from now to run some simulations and explore which latitudes have, in average, higher visibility times over the ISS, the International Space Station. So I leave it here. Feel free to download the worksheet here in this link. So you can have all these exercises, all these activities, and some tips on how to launch these simulations on your desktop. So I'll leave it here for 5-10 minutes, and also feel free to make any questions in the chat, in the live chat, if you have any. I'll see you in 5-10 minutes from now. So let's say, well, I don't know in which parts of the world you are in right now, but yeah, let's say this is 38 now. Here 10:38. So let's do it at 45 more or less. So 10:45 UK time, wherever you are in the world. Let's agree. 5-10 minutes from now, let's resume activities again, and feel free to start solving this first challenge of today. See you in a bit. Okay, so let's resume activity. Let's resume to the second.
Yes, yes, we can hear you. I think right now it's muted.
Right. Can you also see my screen?
Yes, yes, it's visible, but your camera.
Perfect. Okay. So let's
All
move.
right, this looks
If
good.
that's okay with all of you, I hope nice break. Perfect. Let's do this exercise of the ISS. I don't know if some of you had the chance to the simulation. Yes, we can go through it. Okay, I couldn't understand. Okay, I see that some of you had problems, but did you all manage to log in with the credentials? If anybody has any issue, please let me know. So, okay, so if you go and enter, I see no, sir. Yes, sir. Okay. If it's if it's yes, it's okay. I will understand the silence as a yes. If no, please let me know because you should be able to access with the credentials I gave you. So I'm going to put the link here again, and the username and the password are the ones that you can see there. Okay, so maybe let me see if I can change my screen so you can see the application and you can see what you should be doing in this exercise. So this is gonna be helpful for you as an introduction to some of these tools that we use internally to develop space missions and to do space mission design. Perfect. So if you can see my screen, that's what you should see. That's what you should see. See if it goes. Okay. So that's where you should be landing. You should be writing a Starman and the password that you have also in the chat. And when login, it might take a few seconds, but then you enter to the main portal of BApp. So here is where you will be able to launch simulations and do mission analysis as we've been doing. Remember that these credentials are for demo purposes. And remember that this is the old stable version, BApp. We have a new version. It's called OpenApp that is still in beta mode. I'm going to put you the link here as well. There we go. So you can log in directly in the new version that is in beta mode by signing up directly there, and you will be able to create your own user and password, so your own credentials. Let's see if it goes because I have so many tabs open. Okay, it looks like okay. There we go. So you should be able to access two modules. The MSD, the Mission System Design, and the Hardware in the Loop module. These are the two main ones that we're going to mention today, especially the MSD module, the first one that you see here. To access the MSD, the Mission and System Design module, I'm sure that some of you already probably have access to it, but once you land in BApp, you have to write a program name and a mission name. This could be, I don't know, the Copernicus program. If you're playing with constellation, this could be the bio research program. And as a mission name, this could be satellite to the moon, or low Earth orbit, or above Van Allen belt. I'm going to put the LeoSat with the constellation bio that I just defined. So you need to put one program name and one mission name, and then click on Go. Just for information, this is a set of ground stations that you could be using with their specifications, and the rocket launches that you could be launching with. So here are the next rocket launches in which we could be launching our satellite, our constellation, in case there are orbital constraints in terms of inclination or specific sun-synchronous orbit and so on. You see here the limitations, so you can be aware of which orbit you could be aiming at in each of these launchers in terms of altitude and the orbit itself. So you have to put a program name and mission name and click on go. Once you do this, you enter these two modules that I was showing before. And you have to define your satellite mission. You have to choose your satellite platform. You have to define your payload. This is done quite easily by clicking on the icons. It looks very simple, but the simulations are very realistic. So here we take into account the solar cell surface, the shadowing between the main body and the solar panels, and so on and so forth. So the simulations you're going to be running, they are quite detailed, quite realistic. I'm not going to go. Yes,
but your screen has stopped. Like, I mean, the screen share is not happening.
So should I try to share again? So you could not see my screen?
No, not at the moment.
Since when? Or could you follow until a few seconds ago?
I guess, yeah, now it's sharing, yes.
Okay.
Yeah.
Well, let me know if you missed some of what I was saying. I was running through VApp from the portal all the way. So I was defined. So I'm going to exit here for the ones in case you haven't seen it. So I defined the program name. This could be the constellation biology for our mission, and this could be the LEOsat. And then we could have a moonsat or a marsat. And I click on go. It's important that you fill these two fields, and then you click on go. Then you can select a spacecraft configuration. You could be choosing and defining your payloads. In our case, we could define the power that we need, the data that it generates. That before I saw 3 gigabytes per second, that's quite high before. You could be defining altitude modes. If these payload modes can be active in daylight, in eclipse, define your field of view if you have any optical instruments, where you allocate the instrument. There are a lot of things here, but we can skip this payload tab. And the goal is to go from platform to payload to mission to simulation. In the mission tab, you could be defining regions of interest, and you can also choose from a map a particular ground station. So I'm going to choose one, I don't know, in Singapore, for example. So you need to select one antenna to operate your satellite, and then to launch a simulation, it's quite easy. Here you will see ISS. We're going to leave the ISS from now. You see that the inclination is 51.6 and the eccentricity is 0. It's pretty much 0, so it's pretty much a circular orbit. So to launch the simulation, we only have to write the start time. If you write now, NOW, so now, as soon as I click on the W, my local computer time, it's input automatically. So write now or write any of the, in any of the formats that you see here in the information pop-up, and launch a simulation. I'm going to simulate for 1 day. So I'm going to put 1 day simulation, and I will click on simulate. When I click on simulate, you will see there's these 3 dots. So it's when the simulation is being launched. So what happens is that we send a request to our backend. The simulation is launched, and in a few seconds, we get all the results. So you don't need to install anything. You don't need high processing computing capabilities. You can even do that in a smartphone, depending on the smartphone model. And that's it. We have power budget, link budgets. We have visibility times on the ground station. So we can go to Singapore and see which is the acquisition of signal, the loss of signal time, the definition of total passes for this day that I've simulated, the minimum, maximum, average revisit times, pass times, and so on and so forth. So there's a lot of information that has been computed, and then you can display. Also, in terms of the points of interest, regions of interest, I haven't defined any, but you can play around with all this. So I hope that this is clear and that you managed to launch some simulations. Everything is well described in the worksheet. So if you have a look at the worksheet, you will see that all the information is there. Perfect. So let's go back to the slides. I recommend you to open two tabs, one with the presentation and the other slide, the other tab or the other window with BApp. And open as many as you want. So BApp allows multiple users, so you can run multiple simulations in parallel if needed. So you can have different tabs with different simulations running in parallel. Okay? Perfect. So I'm mindful of time. I will launch this challenge to you. This is the bonus question that I put it there. I asked you before the break. So let's see if you have answers for this. Let's move on the presentation slides and let's see. So open a new tab with a poll everywhere. I hope you still have it open so you can answer this question there as well. So essentially, the challenge question here is for you to answer in which latitudes it's better to observe the ISS. Is it in the equator? Is it in mid-latitudes? Or is it in polar latitudes? As you've seen probably in BApp, the inclination is 51 degrees or something like that, 50-something degrees. So that's the inclination of the ISS. So if you launch a simulation as I've done, you should come up with some conclusions. You will see the orbital track of the ISS. I'll leave you a few seconds and check the chat meanwhile. I'm going to share again login credentials because I see that some people, maybe you entered now recently and you didn't have the username and the password. If it shows you login and successful, it's because probably you haven't typed well the password. I'm not presenting. Okay, I think we solved that. You can see my screen now. Okay, some of you are asking to explain the app again. You can write any name. It's very flexible and it's very simple. So play around with it. Try to break it. This is the link again. The username, let me write it again. Username is Starman. And the password that you have to write to log in, it's Planet Mars. I think it's Planet Mars 09. It was, I think. Okay. Right, so try to log in with these credentials again, the ones that you have. I assume that most of you have managed to launch simulations on the ISS. So if you download the worksheet with the link that you saw before, I think it was shared as well, you have all the steps there. So don't worry, you will have this at a later stage, so feel free to play around with it. I'm going to move on as a matter of time. I see that most of you got it right, mid-latitudes. So if you do these simulations and you put different points of interest, if you choose ground stations in different latitudes, so if you choose Singapore as one antenna, as one ground station, if you choose Fiumicino or Puerto Llano in Madrid or Panama, and then if you choose North Pole or S-range or one of these polar latitudes, and you run the simulation of the ISS, you will see that your average visibility pass in each of the passes is in average 1 to 3 minutes better in mid-latitudes than in equatorial latitudes. So for the ones of you that answer polar latitudes, you got it wrong because the ISS doesn't fly over the poles. It only reaches 50-something degrees of latitude, and then it goes to the equator again. So the right question is V. So well done for 68% of you. Being in mid-latitudes have those latitudes in average, they have better visibility, so the ISS fly over them with direct line of sight higher, longer periods of time. So more visibility times to see the ISS in those latitudes. In the equator it also flies, but also pretty much the same amount of times. But the periods of time in average overall are a bit less. And you will see there in one of the tabs, just the one I showed you before, that the average time it's a few seconds sometimes or minutes in some others, depending on the total time of your simulation. Perfect. So well done. Really well done. Let's move on to the rest of the content. So we've been touching base with a spacecraft, essentially the satellite that is composed by the payload and the platform. We have started to get a bit some insights regarding orbits, and now we're going to go into a bit more depth in orbits. And then we're going to touch base also on the ground segment and the launch. These are the main key components to finalize the design of our mission. So we already defined a bit our payload, our platform, a bit our satellite, and now we are going to do this exercise of getting more knowledge about orbits that are essential in a space mission. So here you see the main rules on orbits. You can so the orbits they are normally ellipses or they are circular orbits if the eccentricity is 0, but always those disks, those ellipsoids, in their plane, in their surface, they have to contain the center of mass of the body. So that's why you see a tick in the beginning. So there cannot be orbits on top or on the sides of the center of mass. And obviously they have to be in ellipses or circular orbits. They have to be circles at least. So no triangles and no weird shapes unless you have crazy propulsion systems, which is not the case normally. So here you see in green, geostationary orbit. So it's a geosynchronous orbit that basically what's happening in that green dot is that it's all the time flying over the same point on Earth. So it rotates at the same speed as the rotation of the Earth. And this is exactly one disk. So there is only one disk around the Earth above the equator that it's around 36,000 kilometers. And if you place a spacecraft there, you will always be flying exactly over the same point on Earth. And we're going to see that in the next exercise that we do. In blue, you see Middle Earth orbit, so MEOs. Those are quite similar to perhaps the GPS or Galileo constellations. They have inclinations, of course, but the altitudes are perhaps, they're above, I think, a few thousand kilometers. So the Galileos and GPS are around 22,000 kilometers, and we're going to do some simulations now with some of these orbits as well. And then we have in red LEO orbits. So that dot is in a LEO orbit. The size of the spacecraft, obviously, it's not in scale, but that helps you understand that the closer you are to the body, the faster you rotate, and the higher, the less. Relatively, let's say, the less fast you rotate. So you can see the red dot going super fast, such as the ISS. The ISS rotates between 15 or 16 times a day. It has inclinations. So this one is on the equator. This would be inclination 0 degrees, as you can see, all these three orbits. So the ISS has that altitude. So it's very close to the surface of the Earth, 400 kilometers above the surface, more or less, approximately. And this has inclination. So those LEO orbits are the ones that normally are aiming the small satellites, such as ours, so the Cubesat satellites. So our satellite could be going to, or one of them from our constellation could be going to a low Earth orbit, another one could be going to geostationary, and as we defined before, the others could be with human cells, could be going to the moon and Mars. Perfect. So a couple more things about orbits. Here you can see a perfect example of eccentricity. So here the period of these two orbits is exactly the same. It takes the same time to go around the Earth in these both satellites, but one has eccentricity 0, which is the red one. It's a circular orbit. And the other one, it's not 0, the eccentricity. You've seen in BAP that there are 6 parameters in the orbit that you can define. If you have chosen the ISS, or if you left it as the ISS, all the rest of the parameters have been frozen because we know the exact position of the ISS. But if you choose polar orbit or sun-synchronous orbit, you will see that only some parameters are frozen. For polar orbit, it's 90 degrees. For sun-synchronous, they depend on other parameters. So you've seen in BAP that this is simplified a bit. You can also input the parameters in a TLE format that it's used sometimes. But what I want to enforce here is that the closer you are to the center of mass, you will see now the white dot that is approaching the Earth, and you will see that the speed gets faster and faster, the relative speed. So now it goes super fast. Well, super fast. That's relative also evaluations. But here it goes much slower. You see, when we are far away from the center of mass, we go slower than when we are closer to the center of mass. And this can be quite helpful if we want to revisit areas or if we want to fly over certain areas of the Earth more time than in others. So there are the Molniya orbits that were used by the USSR. Those satellites that they had high eccentricities because they were flying most of their time. When they were flying slower, they were more far away, but they were flying slower, so they could have more time flying over Siberia and over Russia because the Russian territory is very big. So these are some examples of these orbits being used. I'm not going into a lot of details regarding the parameters. You've seen that in BAP, they are kind of simplified. You can put the altitude instead of the semi-major axis. The inclination is explained there, the eccentricity. So there are these parameters. There are normally 6 parameters that define your spacecraft position, your orbit position in place and in time. So in position relative to the Earth. You can get much more details and information. I think in BAP there is in the user manual or anywhere where you put orbital parameters. They can get quite tricky, but in BAP are simplified. Just one highlight about the SSO, the sun-synchronous orbits. They are very relevant and very important because they, especially for remote sensing and Earth observation, because they fly over specific regions, over the points on time, with the same illumination at each time they fly. So some examples are the 6 a.m., 6 p.m., which means that at 6 a.m. and 6 p.m. they fly a specific place with the same illumination. So if you take images every now and then, you get all these images for the same for the exact same location with the same illumination. So you can compare between them. And this is an example of a sun-synchronous orbit in which it's the down dusk orbit that you are pretty much in the edge between the sunrise, let's say, and the sunset. So they are quite relevant, I would say, especially for Earth observation and sensing to measure the climate. Perfect. So just to finish on the orbit sections, the orbits are very relevant to how much power I can use in my mission. So to assess if I can provide enough power to my payload, for example. So you see that you need to make a balance between the energy generated in red, where you have sun illumination in your spacecraft, in your solar cells. This has to be bigger or equal to the power needed by the subsystems to keep the spacecraft alive from the platform side of things, and to provide enough power to the payload so that our instruments, our microgravity sensors, our accelerometers, gyroscopes that we were talking before, our cameras or optical instruments to measure the cell growth and all that. So all the power that those sensors can be fulfilled by this very basic formula that obviously it has more constraints. And this has an impact on the attitude of the satellite. On the platform side of things, the orbit is critical here. We touch things on mission, on the payload that we have defined. So here you see that the requirements that we have defined has an impact on all these matters here. It's very important to have the proper power budget. And in BAP, when you run the simulations, one of the graphs, it shows you the battery. So if you see the battery being drained down, so if you see the graph down, this is bad. We cannot launch a satellite that in a matter of hours or days, you consume all the battery power. So you need to make sure, especially in low Earth orbit, that you have eclipses, that during the eclipse, discharge the battery, but not below, I would say, 90, 80, 70%, because otherwise your lifetime, your potential mission lifetime decreases a lot. So that's important. important. The power budget, it's very important. Great, I'm mindful of time, so we're going to do the constellations into the second hands-on activity. This goes into navigation constellations. So we're going to simulations of GPS satellites that have very similar orbits to the Galileo satellites. So you see here 23,000 kilometers of altitude approximately. We're going to be simulating Beidou navigation constellations. So you see the orbital parameters here. And also we're going to run a simulation with an EGNOS, which is a navigation satellite constellation of a few satellites, only 2, I think, or 3, not many of them, but they are in geostationary orbit, and they support getting precision on your position. Perfect. So the concept here is the same. Open another Windows tab, another Google Chrome, Mozilla tab, and try to launch these simulations. You have this in your worksheet. So if somebody can help me sharing this link again, so you can download this in PDF, that would be great, because there you have all the steps explained. So you have to launch 3 different simulations to assess and to be able to answer this question. Some of you might already have an idea, but I will leave you a couple of minutes for you, or maybe 5 minutes, these simulations. Bear in mind that here you need to put the 1st of January 2020 at 12 a.m. if you want this exercise to be done in a simple way, because if you put this start date time, that's going to simplify inputting the orbital parameters that you see in the table. So try to define points of interest by clicking on the map and storing them, or by choosing ground stations in those locations more or less, and try to launch these 3 simulations. The objective here is to answer this exercise, the following exercise. If you had to take a plane somewhere in the world tomorrow or later today with your smartphone, so let's do the assumption that the smartphone can get all the navigation satellite signals. So you can receive GPS, Galileo, Beidou's, GLONASS, EGNOS, and any navigation satellite that is already available in space already, currently available. So if your smartphone could support that, and the assumption that the more navigation satellites that you have on a line of sight, the more signal that you get from those satellites, the higher your precision is, so the better your precision is. So taking this assumption, it's a very rough assumption, but let's do this assumption. That the more satellites that I have flying over me, the more navigation satellites that are flying over me, the higher the precision, the accuracy is in my Google Maps, for instance, or in my positioning application in my smartphone. Where would I fly to? In which continent I would get better precision? Yeah, that's a tricky question. It's not very straightforward, but if you do the simulations of these 3 constellations, you can open as many BApp accounts as you want and launch them in parallel. If you fail simulating, just click again, because there might be a lot of simulations happening now in parallel. So if you do these simulations, you should be able to spot some differences between these constellations, some patterns, and that it's going to help you answering this challenging question, which is basically in which continents there are more satellite navigation satellites flying over them. In which continent? So where would I fly to if I want to get the highest positioning accuracy with my smartphone? Perfect. I'm going to give maybe more minutes with this slide, maybe 1 more minute, because you have all the worksheet. So I'll try to copy the worksheet meanwhile, the link there. I'll leave you a few more minutes, and then I will put the poll, the online poll, so you can answer. Okay, yeah, thanks for sharing the link again. Perfect. Yeah, I was about to put it. I see you already have it. So don't worry if something doesn't work. Go to the worksheet, check the steps that you need to follow, and run the simulations. These are quite applicable to the reality, so it's going to help you understand why the GPS, Galileo, Beidou constellations are choosing those orbits, why those orbits and not other orbits, and which areas they are covering. Do they care about the polar latitudes, Antarctica and the North Pole, South Pole? Are they more interested where more population is based? More interested in specific regions or not? And so forth. Perfect. So I see that you have the worksheet link there. So I'm going to make the poll slide. Even if you haven't managed to run all the simulations, try to do this exercise and answer them just by going by your instinct. Which continents do you think that they have better positioning, I would say, or that they have more navigation satellites flying over them? Wow, okay, I see Asia, America. You will see that you can answer two. So that's a key tip I'm giving you. You can see you can answer two continents because there are two right answers to the question. So that's why you can select two continents. But the key issue here is answering why. Why these two continents? So I see it's winning Asia and Europe. Oceania is still in zero. Antarctica it's 4%. Africa 4%. Okay. I'm gonna leave a few more minutes. But it's important that you do the reasoning behind it because it's quite interesting. When you launch the simulations, you're going to see that there are some weird things happening. And I'm going to cheat here a bit, but the last one, the EGNOS, you will see it's one dot. Even if you simulate for more than 1, 2, or 3 days, you will see that it's in geosynchronous, it's in geostationary orbit. So this dot doesn't move. This means constellation that is composed only of 2 or 3 satellites. It's only a few satellites. They don't move from specific points on the Earth. This means that they can map all of them. So the last satellite doesn't provide a lot of information, to be honest, but it's just for you to simulate a geostationary orbit satellite, see where it lands, where it's flying above. Okay, yeah, mindful of time, so let me give you the answer here. The answer to this question, well, the intuition tells you that GPS is the most widely used and so on, so America has the better coverage in all this. The reality is that both Galileo and GPS, if you launch a simulation of the Galileo satellite, it's similar to the GPS, you will see that they fly over the same regions all the time. If you launch a simulation of 2, 3, 5 days, you will see that they map pretty much all the Earth except the poles. So Antarctica is not a good place to get positioning. So there are smartphones in Antarctica or in the North Pole because you will not get proper positioning there. And another interesting insight. So GPS and Galileo, they cover pretty much all the continents except Antarctica. So that's discarded. So I go there, very good. The one that makes the difference is the second one that you have there, Beidou. For the ones of you that have launched a simulation of Beidou, you probably have seen that you see a bow tie, like an 8 number. Even if you launch a simulation for 1 week, you will see that the 8 doesn't move from there. So this is a bunch of satellites. This is lots of satellites. They fly all the time doing that 8. So those satellite constellation, it's not moving from that part of the world. This means that from the US, you cannot get signal from those satellites of the Beidou constellation. So in Eastern Europe, you can get Beidous, I would say, but this is pretty much in Asia. Why? Because it's a Chinese constellation. So the Chinese constellation, it's only taking care of having positioning in China. And as the gravity, because of gravity, all those satellites that are flying over China, they eventually need to pay the price of having a latitude higher, an inclination higher than zero. So they have to pay have to go south again, which means that theoretically there are more navigation satellites flying over Asia, and because of the loss of gravity, those satellites, they also fly over Australia, Oceania, more or less. These very rough estimates. So there are the GPS and the Galileos, they fly map pretty much all the Earth. And GLONASS, I would say pretty much, it's not making that big difference. But the Beidou constellation is only in that part of the world. So Asia and Oceania are the continents that have more navigation satellites flying over them. That's the conclusion of this exercise. So I hope it's interesting, good to know. So potentially you have better perception of areas of the world than anywhere else because you have more navigation satellites flying over your heads if you go there. Perfect. I'm mindful of time. I'll try to speed up. Regarding the ground segment, you probably have seen this screenshot, this analysis that the app gives you straight away. There they go linked to the frequency bands that we would have to use. With the small satellites, we use UHF, VHF, and as a baseline S bands. So these are the frequency spectrums that you see over here. So around 2 gigahertz, more or less. And if you need more data to be downlinked, so if you have higher data constraints or demands, requirements on that, you might go to X bands or even bands. But those require higher power as well. So you have to pay the price of downloading more data. I would encourage you to build your own ground station. There is different initiatives. As a matter of fact, I've been, during the lockdown, I've been building with a bit of wires and a very cheap SDR, a software radio. I've been building my own ground station, and I'm listening to some satellites. Some of them are the NOAA satellites that they send images of the Earth. So that's very interesting, and it's quite exciting to see in a matter of 10 minutes pass how you can download all the image taken by in real time and see the clouds and see how's the weather in your continent, more or less. So you can get a full picture of this. It's very interesting. So normally in the small satellite, we use antennas, small dishes of 2-3 meters perhaps of diameter, or antennas like that for UHF and VHF. Not as big as these ones. These would be more used for deep space if we were going to Mars or the moon, or higher data transfer requirements. Core budget. Now I'm going to mention the link budget. You will see in VApp some of the graphs regarding the link budget, so you can see the memory, all the data that you are storing, and all the data that you are downlinking. If you zoom in some of the graphs and you make them big, you will see the link budgets there. So that's calculated straightforward. That's very important to take into consideration during a mission design, when designing your mission in phases 0 and A, especially. So here you see that the total data that you can download over a ground station pass, here you see it in green or blue, has to be bigger or equal to the total data generated by the spacecraft, by the platform, which is what we call housekeeping data, to make sure to monitor all the systems in the spacecraft, that everything is going, plus all the data generated by the payload. In our case, it would be cells, it would be data microgravity levels, from the accelerometers, the gyroscopes, and all these images that would require more data to be downloaded. And all aspects have an impact in the ground segment that we select, in the antennas. How many antennas do we need? Where do we choose them on the Earth? And all that. The last exercise focuses on that also. And this has an impact on the platform, the orbit, mission, and the payload as well. So that's it. Let's jump to the last hands-on activity. It's regarding Earth observation and simulating a pseudo Copernicus mission, a pseudo Sentinel-2 mission. So these are very realistic parameters from the Sentinel-2 satellite that we will do an exercise to squeeze this satellite into a Cubesat form factor. So those are very realistic numbers in terms of the satellite. And questions here. We're not going to answer two of them. I leave the first one for you to guess, which is deciding which is the optimal satellite platform configuration for this particular mission. If it's a 3-unit, a 6-unit, or a 12-unit mission. You can answer this by running this challenge, running this simulation on BIAP, and it's a bit of a trade-off. So it's quite an interesting exercise to find out which is the best configuration for this specific mission. And the second one, the one we're going to answer now very straight away because we're running out of time, is which ground station set is sustainable regarding data memory. And here, I'm not going to ask you to run the simulation. At this stage, probably you know better where to see the satellite. So this satellite it's in a sun-synchronous orbit, as you can see here. So for a sun-synchronous orbit satellite, where is it better to place an antenna, a ground station? In the polar latitudes or in for polar or sun-synchronous orbits? So is it better having antennas in the North Pole and in S-range, for example, which are quite higher latitude? Or would it be better to use Singapore and Panama, which are pretty much in the equator? That's the question I'm making here. It's one or the other. So think about the geometries that we've been simulating for polar orbits and for sun-synchronous that are all the time flying above higher latitudes. Would it be better to allocate the ground stations in the equator or in the polar orbits? Okay, I see some answers that say the equator, some others, now it's a bit tight. So it's tight here. I'm going to win. I'm going to give a few more for you to answer. Now it's 50-50. Oh, the equator has been winning for a. Okay, there is no winner. Okay, now we have a winner. It's the equator latitudes. Okay. So most of you think it's the equator latitudes. Northern latitudes, now it's winning a bit. So think about for polar orbits and sun-synchronous orbits. So imagine the Earth is just spinning around, and those satellites would be flying over the poles. Where would you put an antenna to maximize the visibility over your satellite? So it's the northern latitudes. Why? Because the closer you are to the pole, the more frequently fly over you. So if you are in low Earth orbit, you could be even having 14, 15, 16 passes over your heads in the poles. So you want to put antennas in the poles for sun-synchronous and polar orbits, which are basically most of the Earth observation and remote sensing missions to our climate, our climate change, the performance of how are we doing with the CO2 emissions and all that. So keep that in mind for future mission simulations and analysis. And you can see that very easy in BIAP. If you choose those different ground stations and you launch simulations, you will see that your satellites in sun-synchronous orbit, they fly more over the poles than in the equator. In the equator, you would have to wait a few orbits to get another pass, to get the satellite flying over you again. These are graphs that you should see regarding the power budgets, link budgets, visibilities, eclipses times, and all that I'm sure that you've seen already in BIAP. So feel free to answer some of these challenges in more and run more simulations. Just to finish regarding rockets, I'm not gonna. I already mentioned some things about solid and liquid propulsion, but we are quite excited to see these new players, especially with the small rocket segment, enable launching more satellites and smaller to more tailored orbits. I'm sure you know SpaceX, the Falcons, Blue Origins, Rocket Labs, and all that. So there is a lot of rockets, and we're quite excited to see that those rockets are getting reusable and more flexible to be used to launch small satellites as well. And these are how things look in space. So normally there are boxes with the satellites inside, what we call deployers. And once the upper stages of the rockets are in the right place, they eject these small satellites in those normally low Earth orbits. And this graph is just to show you that the private sector is it's been taking over recently. So you see in green that the spacecraft launched, now it's not driven anymore by countries itself. They are also driven by private companies. So it's quite exciting times in the space industry. Perfect. And just to finish, just a few remarks regarding space law. You need to comply with a whole set of requirements regarding the bureaucracy or paperwork aspects of things. So you need to allocate the frequency that you want to use to communicate with the satellite. So you have to coordinate with the ITU, the International Telecommunications Union, reserve your frequency bands in the frequency spectrum. So you have to comply with that. That's normally a bottleneck with the small missions because it doesn't take lower than 6 or 9 months. So you have to plan in advance. And we hope that these processes can be done in a faster way, because right now it's a bit of a bottleneck in a space mission to reduce the time to orbit, especially with the small satellites. You have to comply with your country permission. So at the end of the day, a country has to agree that you launch a satellite. They have to sign or to agree with it. You need to have a third party, normally liability. So the insurance aspects of things. Sometimes there are restrictions on the export control, ITER regulations you have to comply. And very importantly, the debris mitigation regulations. So you have to work on a space debris mitigation plan, a space debris mitigation report. So you ensure you have to comply with the 25 lifetime requirements. So essentially, after your operations, you have to deorbit to re-enter in the atmosphere, especially for low Earth orbits, after 25 years, so below this 25 years requirement. This is quite easy with the small satellites in low Earth orbit because normally, naturally, they decay. So in a few years, even without propulsion, if you are below 600 kilometers mostly, you re-enter in a few years. So at the end, all the spacecraft, our spacecraft would end up burning in the atmosphere. It would be a little shooting star somewhere in the Earth. So we would not be polluting the space environment in the sense of we would not stay there forever. We would re-enter and burn in the atmosphere. For geostationary orbits, it's a bit more tricky. There is a graveyard orbit 200 kilometers higher that you have to comply as well. So that's why you see a lot of dots in red, which is the geostationary, of dots around it, because there is big spacecraft there. They cannot be brought back to the Earth to re-enter. So they are deployed in a graveyard orbit that's set, so they don't take space in this geostationary disk that I mentioned to you before. That's quite relevant to conduct specific missions. Perfect. So that's it. I hope you enjoyed this workshop. We went 5-10 minutes away from the time, but I hope you managed to get familiar with some aspects regarding mission simulation and analysis and space mission design. I hope you are a bit more confident than at the beginning. I hope now you have a set of tools, you have access to the app, so you can get more familiar with all these concepts. There is a user manual on the top right that you can get more. I think there are some demo videos or some more insights in all these topics that we've been touching base. And I'm going to put here in the link, in the chat, the link to the next version, to the new version, which is called Open App, that you can sign up again, and it's much more capable. So you can do simulations of constellations, and you can generate reports in PDF, and you can do much more things. So feel free to go there and explore further any aspects you want to understand better on space missions in general. So I just left the link there. If you go there, there is a sign icon button. You can just click there and you can log in there. So you only need to put your names and your email, and I think that you will have access to some of the modules of an app that is the next version of the app, and it's still in beta mode. So we hopefully will soon release it. But you will still be able to use B app to finalize these workshop activities and challenges that we proposed. Perfect. So I see that the scores are much higher now. I'm happy to see this. I don't see any more zeros or this. So okay, now there is one I guess person that answered 1 or 3, but I see much more people 6, 7, 8, 9, especially even 10s. So I'm happy able to see that after 2 hours, you see that it's a bit higher, that at least you feel more confident with all these topics. You have access to some tools. We've been doing some hands-on activities, some simulations, some analysis, some reading. You've been answering some questions quite good, most of them. So well done for that. Congratulations. And yeah, we encourage you to stay in touch with the space sector, with the space domain, because it can really contribute in improving the world we live in solving global challenges that I was mentioning at the beginning. And I'm sure that that any of you can contribute into that. So thanks for your time. Thanks for joining today in the workshop. Thanks to the organizers, of course, Sujay, Nikita. Well done with all your activities during the World Space Week and for setting up all this. And I hope that you, all of you that this workshop. Thank you very much for your time. And yeah, once again, congratulations for having stayed until now running all these simulations and for answering all these questions. So I leave it to you, Sujay, to close the workshop.
Okay. So thank you, Danny. That was a wonderful session. I'm sure that everyone got they learned something new today. So thank you so much for that. And so we have a closing ceremony later on. You can join at 2:00, and we will be announcing all the winners, and we'll be telling you more about what is the programs and what are the other things you can proceed. Like if you want to learn something, how and what you can learn, all those things will be talked about in the closing ceremony. So again, thank you so much for joining and explaining the students, and I'm sure that they learned a lot of